Hello, welcome to the lecture series in quantum mechanics. Today I am going to discuss the wave function, physically acceptable wave function, and probability of finding the particles. As we know that the quantum mechanics is the study of the dynamics at its fundamental level, and the state of the particles such as position, momentum is described by the wave function. So the measurement in the quantum mechanics is a crucial things. So the wave function play the important role to describe anything of the system. So let's start with the wave function. As we know that the wave function is a mathematical function that that shows the state of the quantum mechanical system and contains all the information regarding the system. So, what is the physical significance of the wave function? So, as we know that the wave function psi r has no physical significance. That means we cannot measure only the wave function directly, but mod psi square give the position probability density of the particle. So, similarly, if we want to calculate the probability of finding the particle in a region x2 x plus dx, so the mod psi square dx gives the that probability in a region dx. Similarly, integrating over x1 to x2 mod psi square dx shows the probability of finding the particle at time t in a region x1 to x2. After that, let's start with the normalization condition. So by knowing the wave function, we can calculate that the wave function is normalized or not. So here the integration over all space psi star r psi r d tau gives the normalization condition. After that, the wave function which I get is physically acceptable or not. So here there are first four conditions that we can identify the wave function is physically acceptable or not. So first one is the wave function psi r must be finite in all space. This means that for bounded wave function, the wave function must be 0 at the boundary, means at the plus infinity and at the minus infinity. And if the wave function is like a scattering wave function, so it must be finite. After that, the second condition is that the wave function must be single valued continuous in all the space. And third one is the derivative of the wave function also must be finite, single valued and continuous in all the space. And last one is the wave function must be square integrable. Here we can see all these conditions by these graph. In figure 1 here first, here we can see at point here, let's say x1, the wave function have multi-valued form, because here we can get y1 and here we can get y2. Similarly, we can get here y3. So for one value of x, we can get three value of y. So this is the multi-valued function. Similarly, in this example, here we can see this function is not continuous. Here, this is a break at the wave function. After that, in this figure, we can see the wave function is not finite, because here we can see at that point, let's say x1, at this point the wave function goes to the infinity, and in the last here we can say this is not differentiable at that point, because we can get two slope at that point. So this is not differentiable. So these type of wave function are not acceptable. So in the after few time I am going to discuss how to calculate or how to check the wave function is physically acceptable or not. After that, by knowing the wave function, we can calculate the probability. Here, first and second I have discussed earlier, and we can calculate the probability of finding the particle in a region between x1 to x2. So probability is given by integrating over x1 to x2 mod psi square dx and uh, divided by integrating over all space mod psi square dx. So we can calculate the probability if the wave function is normalized, so this value will be 1. So let's try to solve some problem on this, how to find the acceptable wave function, how to calculate the normalization constant, and the probabilities of the system. Hello, welcome to this lecture series. Today I am going to solve the problem on acceptable wave function, normalization, and probabilities. So first problem is on acceptable wave function. So let's see the first problem in which the wave function is given by e to the power plus x and minus x. So let's try to solve whether the wave function is acceptable or not. So here we can see the wave function. This is the e to the power plus x, and this is wave function for the e to the power minus x. Let's check the acceptable wave function. So for the acceptable wave function, first condition is wave function must be finite in all space. So let's check in all space. This means at minus infinity and at plus infinity. Here we can see if the wave function is e to the power plus x. So here the wave function we can see at x tends to infinity, at x tends to infinity, the wave function psi x goes to infinity. Here we can see from figure at x tends to infinity, wave function e to the power plus x goes to the infinity, and at x tends to minus infinity, this wave function psi x equal to e to the power plus x goes to 0. Here we can see the red line. So this wave function is not finite. So e to the power plus x is not finite at x equal to plus infinity. So this wave function psi x is not acceptable wave function. Not acceptable wave function. Similarly, we can check for e to the power minus x. Here we can see this is the graph for e to the power minus x. At x equal to minus infinity, this wave function goes to the infinity. And at x equal to plus infinity, this wave function goes to the 0. So similarly, e to the power minus x is not finite at x equal to minus infinity. So this is also not acceptable wave function. So this is also not acceptable. So let's try to solve the other problems here, like this is the plane wave function. So this is like plane wave. Means e to the power plus ikx or e to the power minus ikx. Let's draw the wave function here. So this is the axis, x-axis and y-axis, and let's draw the e to the power plus ikx. So this is the wave function for e to the power plus ikx. And now let's check the normalization condition or the acceptable wave function condition. So we know that for the acceptable wave function must be finite in all space. So here we can check at minus infinity and plus infinity, and throughout the region wave function is finite. Wave function is not goes to the infinity. So this is the finite region, and here we can see at plus infinity and at minus infinity wave function is finite. So wave function is finite, and it is also continuous, and the derivative of the wave function, it is also finite and continuous. So let's check the square integrable condition. So for square integrable condition means wave function must be finite, like here psi star x, psi x dx equal to finite. So this is square integrable condition. Square integrable condition. So if we try to solve this at minus infinity to plus infinity, e to the power, suppose I have taken it for plus I wave function, so psi star gives minus ikx, and psi x is e to the power ikx dx, and let's try to solve this. If we solve this, here we can see limit minus infinity to plus infinity, and here e to the power ikx, e to the power minus ikx cancel out, and here 1 into dx. So if we integrate this, this gives the plus infinity minus of minus infinity. So here we can see that this is not defined or not finite. So this wave function phi x is not acceptable wave function. And similarly, e to the power minus ikx is also not square integrable. So e to the power minus ikx is also not acceptable wave function. Now other problem is C is like sin x or cos x. Here we can see in the plot, this is the sin x wave function. Similarly, for cos x we can draw like this wave function, but here I have chosen the sin x. So here we can see that at minus infinity to plus infinity, wave function is finite everywhere. So this wave function is finite, because maximum value of the wave function goes to either plus 1 or minus 1. So this is finite in all the space. This is continuous also. So this wave function is continuous. And if we take derivative of this wave function, means sin x derivative is minus cos x. So cos x is also finite and continuous in all the space. So derivative of psi x is also finite and continuous. So derivative of psi x is also finite and continuous. So let's square integrable condition. So this is minus infinity to plus infinity, psi star x psi x dx. So if we solve this, so this integration will be minus infinity to plus infinity sine square x dx, and we can write sine square x in terms of cos 2x, because cos 2x equal to 1 minus 2 sine square x. So here we can write 1 by 2 integration minus infinity to plus infinity 1 minus cos 2x dx. Further, we can write here 1 by 2 minus infinity to plus infinity 1 into dx minus minus infinity to plus infinity cos 2x into dx. So here we can see if we integrate this, so this gives 1 by 2 times only first integration. Here we can see, so this upper limit plus infinity and minus of minus infinity. So this is not defined, and the other integration as well also, because if we put the plus infinity, the value of sin x is either plus 1 or minus 1. So but due to this integration, this is not finite. So wave function psi x equal to sin x or cos x is not acceptable wave function. But we can see in the quantum mechanics, for the infinite potential well, wave function is like under root 2 by L sin n pi x by L. This means that this wave function is finite, or this wave function is acceptable in particular region, means 0 to L or 0 to A or minus L to plus L. In the finite region, this wave function is acceptable, but in all space, this wave function is not acceptable. So let's try to solve the other examples like psi x equal to e to the power minus x square. This is the Gaussian wave function. Here we can see the plot, and this wave function is finite in all space, because here we can see at minus infinity and at plus infinity wave function goes to the 0, and in the whole the space wave function is finite everywhere. So this wave function is finite, and we can see this wave function is also continuous. Now, the derivative of this wave function is also finite and continuous, because minus 2x comes here and e to the power minus x square is present there. So this is also finite and continuous. This means that derivative of phi x is also finite and continuous. Now let's check the square integrable condition. So for square integrable, this wave function must be follow this condition, means minus infinity to plus infinity phi star x phi x dx. And let's try to solve this. So this integration will be minus infinity to plus infinity e to the power minus 2x square dx. And we know that the integration in terms of gamma function, this means that minus infinity to plus infinity x power n and e to the power minus alpha times x square dx. So this integration will be gamma function of n plus 1 by 2 upon alpha to the power n plus 1 by 2. Let's use this integration. So this value will be, here we can see this, here x power 0 is there, so here we can choose n equal to 0. So this will be gamma function of 1 by 2 upon 2 to the power 1 by 2, and gamma function 1 by 2 means root pi, so this value will be under root pi by 2. So this is finite. So the wave function, phi x equal to e to the power minus x square is acceptable wave function. And this is the wave function for the harmonic oscillator ground state. Similar problem is here. This is the wave function for the excited state of harmonic oscillator. This is wave function of excited state or first excited state of harmonic oscillator. So here we can see the plot of the x e to the power minus x square. So this wave function is finite everywhere, all the space, here at minus infinity to at plus infinity. This wave function is finite and it is continuous also. So this is finite and continuous, and derivative of this wave function is also finite and continuous. So now let's check the square integrable condition for this minus infinity to plus infinity. And if we try to solve the psi star x psi x dx, so this will be e to the power minus x square e to the power minus 2x square into x square dx. and use this same integration as I have put here. So here we can see for this integration n will be equal to 2. So this integration will be gamma function 2 plus 1 by 2 upon 2 to the power 2 plus 1 by 2, and this value will be gamma function of 3 by 2 and divided by 2 to the power 3 by 2, and gamma function 3 by 2 means 1 by 2 and root pi and divided by 2 to the power 3 by 2. If we want to solve this further, we can solve, but here we can see this is the finite. So this wave function is acceptable wave function. So psi x equal to x e to the power minus x square is acceptable wave function. So in this way we can solve all type of wave function and we can check whether it is acceptable or not. So now next problem is to find the normalization constant and probability. So here we can see this is the problem number 2. At time t equal to 0, a particle is represented by the wave function psi x equal to a x by a in a region 0 to a, and in a region a to b this wave function will be a b minus x upon b minus a, otherwise wave function is 0. So first part of the question is find the normalization constant. So let's try to solve the first part. The normalization constant, this is the normalization condition minus infinity to plus infinity psi star x psi x dx, and this integration will be equal to 1. So let's try to solve this. So this will be, let's break this integration according to this limit. So minus infinity to 0, the wave function is 0, because here we can see only wave function is there 0 to a and a to b region. So this wave function is 0 in this region, plus 0 to a wave function is a x by a. So psi star psi, if we do psi star psi, so this will be mod a square. Let's write it properly. So this will be mod a square upon a square, and the integration will be 0 to a, and here it comes out to x square dx, plus up next a to b, from a to b, so this wave function will be mod a square upon b minus a whole square. 1b minus a comes from psi star and 1b minus a comes from psi. So this integration will be a to b, and here b minus x whole square dx. After that, from b to infinity, here we can see for otherwise wave function is 0. So this is 0 times dx, and this integration will be equal to 1. So this integration will be 0. This integration also will be 0, and let's try to solve this integration. So here this will be mod a square by a square, and this integration will be x cube by 3, and limit is 0 to a, plus mod a square upon b minus a whole square, and this integration will be, if we assume this is equal to t, so we can get minus sign, so here we can get minus 1, and here will be b minus x whole cube by 3, and limit is a to b. You can check this integration also, and this equal to will be 1. Now this integration will be mod of a square upon a square, and this integration will be a cube by 3, because upper limit a cube and minus 0, so a cube by 3 plus mod of a square upon b minus a whole square, minus 1 is there, by 3 here I have also put. And if we choose the upper limit, so this will be x will be equal to b and b minus b will be 0, minus if we choose a x equal to a, so this will be b minus a whole cube, and this equal to 1. After that, here we can see this is cancel out. So here mod of a square I have taken common, and this will be a by 3, and here we can see minus and minus goes to the plus, and b minus a here whole cube, and here b minus a square, so this cancel out, and here we can get b minus a by 3. So this is the simplified form. Now after that, here we can see b minus a by 3 and a by 3 is cancel out, so this will be mod a square into b by 3 equal to 1. Now if we solve this, we can get the value of normalization constant, so this will be 3 by b, and we can get here mod of a equal to under root 3 by b. So in this way, we can get the value of this constant, normalization constant, by using the normalization condition. Now, the second part of the question is sketch this wave function. So here I have plotted here wave function. So B part I have drawn here. Let's try to draw this wave function. So this is y-axis, and this is also x-axis. And if we see in a region 0 to a, otherwise wave function is 0, so here this is 0, or and suppose this is a. In 0 to a, here we can see this wave function like y equal to mx, because this wave function is like psi x equal to a times x by a. So here we can see this is like y equal to mx, and mx is like this quantity. So this is a straight line passing through origin at this point. And after that, in a region a to b, suppose this is b, if we put b x equal to b or x equal to a, if we put x equal to a here, so here we can see b minus a and b minus a cancel out, and this gives a constant, and this is the value of this part a. So at that point I am here. So if we put x equal to b, so b minus b will be 0. So here we can see at this point wave function goes to the 0. So this is the plot, and otherwise wave function is 0 all the region. So this is the plot of this wave function psi x. Here y equal to means psi x versus x. So this is the plot of the wave function. So part B is there. Now next part is, what is the value of the probability of finding the particle in the left half of the A? Left half of the A means 0 to A region. So let's try to solve the value of the probability in the left half of the A. So part C. So we know that B function is normalized. So the value of the probability is left half of the A means 0 to A psi star x psi x dx. Since wave function is normalized, so we don't we cannot write here like integration over psi star psi means normalization condition. So if we solve this, so this will be from psi star, this will be 3 by b, root 3 by b from psi star, and root 3 by b from psi. So this will be 0 to a, and psi star, here the B function is only in the region 0 to a, only mod of a x by a. So this will be x square by a square. So this will be x square by a square dx. So here if we solve this, 3 by b into a square and integration of 0 to a x square dx. So this will be 3 by a square b, and here this will be x cube by 3, x cube by 3, and limit is 0 to a. Now this probability will be 3 by a square b, and this will be a cube by 3. So 3 and 3 cancel out, a square cancel out. So the value of probability will be p equal to a by b. This is the probability in the left half of the a. Now in this question there are two extra condition is given. Check your result in the limiting case at b equal to a and b equal to 2a. So if we check this probability at b equal to a, now probability at b equal to a, if we put here, so this will be a by a, and here we can see the total probability will be 1. So in the left half is the total probability will be equal to 1, and probability for b equal to 2a, so this probability will be a by 2a, and a cancel out, and the probability will be half if b equal to 2a. Here we can see, we can verify this result also from the graph. Here if b equal to a, if b is a, means this b function a, this position a, this is also will be a. This means this point goes to at that position. So only the b function is like that. So only b function is like this straight line. So in this reason total probability will be 1. So this comes out to be 1. If b equal to 2a, means this distance and this distance is equal. So in the left half the probability of finding the particle will be 1 by 2. So this result we can get from here. Now the next problem is consider the B function psi x equal to a e to the power minus lambda times mod x e to the power minus I omega t, where a, lambda and omega are constant. So find the normalization constant. So normalization condition is the normalization condition normalization condition integration over minus infinity to plus infinity psi star x psi x dx equal to 1. This is the normalization condition, and let's try to solve using this condition. So minus infinity to plus infinity, here mod of a square is comes out because one from psi star and other from psi, and this is the real part. So this will be minus 2 lambda times mod x, and here psi star, so this, because this is complex term, so this will be e to the power I omega t, and from psi this will be e to the power minus I omega t. So e to the power minus I omega t dx equal to 1. So this term cancel out, e to the power plus I omega t and e to the power minus I omega t. So this integration will be mod of a square integration minus infinity to plus infinity e to the power minus 2 lambda times mod x dx equal to 1. So here we know that this e to the power minus mod x, and this is the constant term, so this wave function is even wave function. So here e to the power minus alpha times x is there, and if limit is equal and opposite means minus infinity to plus infinity, so this wave function is even function. If the wave function is even function, we can solve this limit. This means this will be 2 times, here we can write 2 here, so this will be 2 times integration 0 to infinity, and we can write like this for even wave function, and this will be 2 lambda times x, and this, because in 0 to a mod x will be x because it's a positive region. Now this integration is very simple, so this will be 2 times mod a square and e to the power minus 2 lambda times x and divided by minus 2 lambda, and limit is 0 to infinity equal to 1. After that, this is 2 times mod a square, and here 2 and 2 cancel out, we can remove 2 from here, so this will be mod of a square by lambda, and if we put the upper limit e to the power minus infinity, this will be, and this will be goes to 0, and negative sign is also present here, I have put outside, and if we put the 0, e to the power 0 means 1, so this will be minus 1 equal to 1. After that, mod of a square by lambda equal to 1. So from here we can get the value of normalization constant, and this will be under root lambda. So this is the normalization condition for this wave function. Okay. Now next problem is, consider a particle whose wave function is given by psi x equal to sine pi x by a e to the power minus I omega t in a region 0 to a. And the question is here, find the probability of finding the particle in a region a by 4 to 3a by 4. So if we see this wave function, so this is the wave function for infinite potential well. For infinite potential well, wave function is like similar, psi x equal to under root 2 by a sine n pi x by a. And if the potential well like from 0 to a, this is width of the well. So if we try to solve this wave function, we can get this, if we try to solve this potential, we can get this wave function. So we can solve the this wave function to calculate the normalization constant, but here we can see this is the wave function for the infinite potential well. So the normalization constant of this wave function is psi x equal to under root 2 by a sine pi x by a into e to power minus I omega t in a region 0 to x a 0 to a, and otherwise this wave function will be 0. We can calculate this normalization constant also, but I think it is clear, so I am not going to calculate here. So after that, we can calculate the probability in a region a by 4 to 3a by 4. Now mod psi star psi, so psi star psi will be under root 2 by a and under root 2 by a, so this will be 2 by a, and here we can get the sine square pi x by a into e to power minus I omega t. So psi star will be e to power plus I omega t, and e to power minus I omega t, this comes from the side, into dx. So this will be cancel out. Now the probability will be 2 by a by 4 to 3a by 4 sine square pi x by a dx. Now use cos 2x equal to 1 minus 2 sine square x. If we use this, we can get 2 by a, and sine 2x will be 1 by 2 integration a by 4 to 3a by 4, and this will be 1 minus cos 2 pi x by a into dx. So here 2 and 2 cancel out. So now this probability will be equal to 1 by a, and the first integration is like dx, so this will be 3a by 4 and minus a by 4. This is the first integration. Here if we solve this integration dx, so this gives x and upper limit minus lower limit minus. Now this integration of cos x gives to the sin x. So this integration gives the sine 2 pi x by a upon 2 pi by a, and the limit will be a by 4 to 3a by 4. Now put the upper limit and lower limit. So this will be p equal to 1 by a, and here we can see 3a minus a equal to 2a by 2, so this will be a by 2, and minus here will be a by 2 pi this, and if we put the upper limit 3a by 4, so here 3a by 4, so this will be sine 3 pi by 2 minus sine pi by 2. Now sine 3 pi by 2 will be minus 1. So this will be a by 2 minus a by 2 pi, and this will be minus 1, and here sine pi by 2 will be 1. Now if we take a is common, so a will be cancel out, and this will be 1 by 2 minus here this will be minus minus plus, and this will be 2 by 2 pi. Now if we solve this, this will be 1 by 2 plus 1 by pi. So this is the probability in a region a by 4 to 3a by 4 of a one-dimensional harmonic of a one-dimensional infinite potential well. So in this way we can calculate the acceptable wave function, normalization condition, and probability. So in the next lecture I am going to discuss in the next lecture I am going to calculate the acceptation value of the different wave function